Now let's see what is electronic Zeeman effect. Splitting of electronic states under applied magnetic field is called Zeeman effect. This effect is only observed under applied magnetic field. So by seeing this diagram, when there is no magnetic field, you only see one electronic transition is possible, right? But under magnetic field, there are the splitting of three spectral lines takes place and three electronic transitions takes place. So this effect is only observed under applied magnetic field. If you take an example beryllium, it has an atomic number 4 and mass number 9. The electronic configuration of beryllium can be written as 1s2 and 2s2, 1s2, 2s2. If we consider this as an orbit, this is the first orbit 1s2, which has 2 electrons, and the 2s2 orbit has 2 electrons, and the 2p orbital will be vacant because it has only 4 electrons, right? So in first orbital there 2 electrons are filled, and in second orbital 2 electrons are filled, 2p orbital is vacant. Energy can be supplied in the presence of magnetic field as well as in the absence of magnetic field. When there is no magnetic field, that is Bz is equal to 0, when we apply energy, electrons undergo transition from 2s orbital to 3p orbital. But in the presence of magnetic field, where magnetic field does not equal to 0, when we apply energy, the 3p orbitals are present in the third orbital, and electrons can jump from 2s orbital to 3p orbital. So we can observe three spectral lines. Here, if you see, this is the third orbital, right? This is 3p orbital. The last one is 3p orbital. One electron can jump from 2s to 3p orbital. So while jumping, it has three spectral lines are possible. According to three energy states, three spectral lines are possible. So splitting of spectral lines takes place under magnetic field. Now let's see how it happens. If you take 2s, 2 is the principal quantum number and s is the angular momentum, that is L. For different L values, for different L values, the orbits may vary. If L is equal to 0, then it is S orbital. If L is 1, then it is P orbital. If L is 2, then it is D orbital. If L is 3, then it is F orbital. Magnetic moment. M is the magnetic moment. It is the number of electronic states under magnetic field. Number of electronic states that are possible under magnetic field. So under applied magnetic field, the spectral lines are going to split. The number of splitting is given by the magnetic moment. And by using this formula, we can see how many spectral lines are possible. M is equal to 2L plus 1. For 2s orbital, the s value of L is 0. So 2 into 0 plus 1 gives you 1. And 3 for 3p orbital, L value of P is 1. So 2 into 1 plus 1 is equal to 3. So 3 spectral lines are possible in 3p and only one spectral line is possible for 2s. That is what is represented as here. When magnetic field is 0, 2s will go to 3p. Electrons are going to jump from 2s to 3p orbital. When we apply magnetic field, 2s orbital cannot split because they have only one electronic state, as we already saw now. M value is 1, right? So it cannot split. But in 3p orbital, M value is 3, so they can exist as 3 electronic states. So here 3p have 3px, 3py and 3pz. They will be in degenerated state, that is degenerated orbits having the same energy. So within the spectra, they show same electronic state. That's why we can observe a single line under no magnetic field. Under magnetic field, they have different energy. So we can observe 3 energy state of 3p orbitals, that is m minus 1, m0, m plus 1. Okay, so now let's see what is selection rule in another video, in the continuation video. Thank you.